So we have this general concept of what a limit is. If we say the limit as x approaches a of a function equals L, that means as we walk along this function f, and we get closer to the x value x equals a from either the left or the right, our y value of this function approaches L. In short, as x gets close to a, the y value of our function gets close to L. And we learn that it doesn't actually matter what happens precisely at this x value a. As long as the closer and closer x gets to a, the y value of the function gets closer and closer to L. Now this is all well and good, but mathematicians back in the day felt like this concept was a little informal, and they wanted to formalize this mathematics. Well, this took hundreds of years, but eventually what mathematicians landed on is this formal definition using epsilons and deltas that you're seeing in your calculus class today. And I want to give you an analogy that I hope will help you understand this formal definition of a limit. But first, I want to unpack a couple of things. This piece of the definition right here, if we recall our absolute value inequality, we hopefully remember that we can rewrite that inequality like this. We can add L to all three pieces, and we find that this notation up here is just a fancy way to say that our function value is between L minus epsilon and L plus epsilon. So epsilon is just some small positive number, and our function value being between L minus epsilon and L plus epsilon just means that our function value is somewhere in this range right here. So this notation right here just means that the y value of our function is somewhere in this range. How about this x minus a absolute value less than delta? Well, we can do the same thing. And we see that this notation here is just fancy notation for saying that x is between a minus delta and a plus delta. If I drew that up here on this graph, delta again is just some small positive number. So this notation here is just a shorthand way to say that our x value is somewhere in this domain. Okay, now that we've set that up, let me give you an analogy. Let's say that our function is this mysterious Mount Calculus. And Mount Calculus is mysterious because there's this little area that you can get really, really close to, but you cannot actually stand directly on this spot on Mount Calculus. And we all suspect that the altitude of this very mysterious point on Mount Calculus is 1,000 feet, and this point on Mount Calculus is a horizontal distance of 50 miles from Oxford. This is all very geographically accurate. And the Queen of England is very interested in this mysterious point on Mount Calculus, and she wants to prove that the altitude of this very mysterious point on Mount Calculus does in fact approach 1,000 feet. So she calls you in and says, I want you to walk along Mount Calculus near this mysterious point, and I want you to get within 10 feet elevation-wise of that mysterious point on Mount Calculus. Report back to me. And you say, okay, 10 feet. So that would be between 990 elevation-wise and 1,010 elevation-wise. And you walk along Mount Calculus from this direction until you get to that 990-foot mark. And then you come around Mount Calculus from the other direction, and you descend until you get to this 1,010-foot mark. And you report back to the Queen, and you said, I did it. I came within 10 feet of elevation of that mysterious point on Mount Calculus. And the way that I did it is I got within 2 miles in either direction from this 50-mile mark from Oxford. As long as I was somewhere down here within this domain, then that automatically put me within 10 feet altitude-wise of this mysterious point. You pat yourself on the back for a job well done, and you're about to head out the door, but the Queen seems unsatisfied. She says, oh no, that's not good enough. Now I want you to get within 5 feet of this mysterious point elevation-wise. So you go, okay, 5 feet. Let's see, that would put me at an elevation of between 1,005 and 995 feet. And you hike Mount Calculus from this direction, and you hike Mount Calculus from this direction. And you realize that if you get within 1 mile in either direction of this 50-mile marker right here, that would put you between 49 miles and 51 miles. If you're somewhere down here in this domain, then that's going to guarantee that your altitude on Mount Calculus is somewhere between 995 feet and 1,005 feet. You report back to the Queen, weary from your trip, and she's still unsatisfied. She wants you to get within 1 foot elevation-wise of this mysterious point on Mount Calculus. So she sends you out, and you realize that you can get within 1 foot of this mysterious point on Mount Calculus. That would be an elevation between 999 and 1,001 feet. And you can make that happen, I don't know, if you're within a 1/4 mile of this 50-mile mark. You report this back to the Queen, queen, and the queen starts to get a little mysterious on you. I'm going to erase all of this because the queen now says, no, that's no longer 1,000 feet of elevation on Mount Calculus, that's L feet of elevation. And that's no longer 50 feet from Oxford. We're going to define it as some distance A. And the queen decides, I don't want you to get 10 feet or 5 feet from this elevation L. I want you to get a distance of epsilon away from this elevation L. So you need to be between L minus epsilon and L plus epsilon, elevation-wise, on Mount Calculus. And the queen says, can you do it? And you think clearly the queen has gone mad because epsilon isn't even a number. How are you supposed to get a distance epsilon away from this altitude on Mount Calculus we're calling L now? Then you think, well, wait a minute. Maybe the value that the queen gives me for epsilon doesn't even matter. No matter what epsilon she gives me, no matter what level of closeness the queen wants me to get to this elevation L on Mount Calculus, I could do a little calculation and I could figure out, based on the epsilon that I'm given, how close do I actually have to get to this A value in order to achieve the queen's objective. We'll call that distance from A delta, and what I can come back to the queen with is this argument. No matter what epsilon you give me, no matter how close altitude-wise you want me to get to this mysterious point on Mount Calculus, I can find a delta so that if I get within delta distance of this A down here, my altitude will be within the parameters that you've set with your epsilon. And if that's the case, if no matter what epsilon the queen gives you, you can find this delta that's going to satisfy her requirements, then what that means mathematically is that the limit of this function of Mount Calculus as our x value approaches A, that limit equals L. So let's read it out. This limit exists if for any number epsilon, there is a corresponding number delta such that our altitude is within an epsilon of L whenever our horizontal distance is within a delta of A. So let's read it again. This limit exists if for any number the queen gives you epsilon, there is a corresponding delta that you can come up with such that your altitude will be within an epsilon distance of L whenever your horizontal position is within a delta distance of A. And you may be wondering how we find this delta. Well, maybe we take the epsilon that the queen gives us and we divide it by 10. And that delta is sufficient to get us to where we want to be. Maybe we take that epsilon and we multiply it by 5. Maybe we take the square root of the epsilon that the queen gives us. It actually depends on the shape of the function. And we have to do a little bit of mathematics to figure that out. All right, that's it. That's the Epsilon-Delta definition of a limit. It's all just the queen getting pickier and pickier about how close she wants you to get to some y value on a function. Okay, I hope that helps you out conceptually with some of these problems. I'll be working through some Epsilon-Delta problems from your homework and posting those videos as well. All right, I'll see you next time.